Ladies and gentlemen, my name is David Reed. I'm a Vice President and the Biological Secretary of the Royal Society. And I have one preliminary task, and that is to ask you, if any of you have brought your mobile phones, could you please check them to make sure that they're switched off? Thank you. I'd like to wish you a very warm welcome to the Royal Society, both to this audience and to the wider audience around the world who are tuned in to this evening's lecture in the form of a web broadcast. Tonight's lecture is supported generously by the John Templeton Foundation. It's one in a series which is devoted to the nature of human knowledge and understanding. In fact, it's the second lecture in the series. The first one was enormously successful, and we are convinced that this one will be likewise. It's a pleasure also to have in the audience, a particular pleasure, Professor Charles Townes, who has been elected the John Templeton Prize winner for 2005. Welcome, Charles. Nice to have you here. Tonight's speaker is Martin Nowak. Martin studied biochemistry and mathematics in the University of Vienna and took his PhD there in 1989. Immediately after taking his PhD, he moved to Oxford, where he worked for a number of years with Bob May. Bob, of course, as you will know, is currently our president. He is particularly apologetic that he couldn't be here tonight. He is actually, I think, as we speak, lecturing in Princeton. As I say, he would have liked to be here. At least this being webcast, he will have the chance to follow up on the issues that you raise, Martin. After his time with Bob, he was elected in 1997 at the age of 32 to a chair of mathematical biology in Oxford. The following year, he moved to Princeton to establish the first program on theoretical biology there at the Institute of Advanced Studies. In 2003, Martin moved again, this time to Harvard, where he took up the directorship of the program for evolutionary dynamics. Martin has published in his career very extensively and has been the recipient of a number of prestigious awards, to mention just three: the Weldon Memorial Prize, the Albert Wander Prize, and the Henry Dale Prize. While having very broad interests in mathematical biology, Martin's paid particular attention to studies of the dynamics of infectious diseases, to human cancers, and to the evolution of human language, and to cooperation in the human species. And it's on this subject that Martin will address us tonight. So it gives me great pleasure to ask Professor Nowak to present his John Templeton Foundation lecture entitled Why We Cooperate. Martin.
Thank you very much. It's a great pleasure and great honor for me to be here. I have the fondest possible memories of my time at Oxford. I love to come back to England always. I see many old friends here, and I also see many new faces, and the new faces give me an excuse to tell my old jokes. And the first is that I'm a mathematical biologist, and some of you might ask, so what is this? And a mathematical biologist is like in the following story. There's a shepherd and a flock of sheep. And the man comes by and says, if I guess the correct number of sheep in your flock, can I have one? The shepherd says, okay, try. The man looks and says, 83. The shepherd is completely amazed. The man picks up a sheep and walks away. The shepherd says, hang on, if I guess your profession, can I have my sheep back? The man says, please try. Mathematical biologist. How did you know? Because you picked up my dog. So by now you have realized, despite 9 years of being at Oxford, I unfortunately did not acquire an Oxford accent. In fact, my students always told me I sound exactly like Arnold Schwarzenegger. But I have no political ambitions whatsoever. I I would like to talk about the evolution of cooperation instead. So first, what is cooperation? Cooperation is a situation where you have a donor who pays a cost, C, and the recipient gets a benefit, B. So it's an interaction between two individuals, people or whatnot, and the donor pays a cost such that the recipient has a benefit. And we can think of cooperation to occur not only between humans, but also between genes, between chromosomes, cells, organisms, animals, and people. Then the cost and the benefit are in the currency of fitness. And fitness is translated into reproductive success. So you could imagine one cell helping another cell to divide, feeding the other cell or something like this. Interestingly, cooperation seems to be needed whenever there is a major transition in evolution. This is what John Maynard Smith called a major transition. And this is, for example, when evolution wanted to proceed from genes to cells. You have to ask, how did the first cell arrive? There was a necessity for kind of cooperation among the genes. A transition from bacteria to eukaryotes. As you know, the eukaryotic cell is the product of a symbiotic interaction among bacteria. A transition from single cells to multicellular organisms. So we are built of individual cells, a huge number of individual cells that somehow have given up their selfish original program of just self-replication. They don't divide, but instead they support the functioning of the organism. So a famous breakdown of cooperation among cells in a multicellular organism is the somatic evolution of cancer. This is when cells mutate and go back to their more primitive program. And obviously you have cooperation of individuals to form societies. You can think of social insects, but you can also think of the human society. So more than any other species somehow, we have managed to establish cooperation. We are all sitting here sort of peacefully, and this is unusual for other animal species. So we have established cooperation on a much larger scale, it seems, than any other animal. And it seems to be one of our secrets of success. Already Charles Darwin noted that in his theory there was a problem when he wanted to explain cooperation. He argued, he observed that natural selection is based on competition, and he did ask the question, how can it be that natural selection leads from competition to cooperation? He was thinking of situations like the following. There are social insects, and in social insects you have workers that do not produce, but raise the offspring of another individual, the queen. How can evolution design such altruistic behavior? Why should evolution equip animals with a program such that they do not self-reproduce, but instead they help reproducing another individual? They reduce their own fitness in order to increase the fitness of somebody else. Darwin did not really solve the problem, but he anticipated an answer, which was really formulated about 100 years later by another famous British evolutionary biologist, Bill Hamilton, and this is called as Hamilton's rule. And Hamilton's rule is that if the coefficient of relatedness exceeds the cost-to-benefit ratio, then the selection of this altruistic trait will work. This is what Richard Dawkins called the selfish gene. So the idea is that you have a gene, the gene tells you to be altruistic to your relative, and chances are that this relative will also have the same gene. Hamilton's rule was paraphrased by yet another very famous British evolutionary biologist, G.B.S. Haldane, who said, I will jump into the river to save 2 brothers or 8 cousins. And this is because the coefficient of relationship with your brother is 1/2, with your cousin it is 1/8. And here you see G.B.S. Haldane addressing a group of British workers. He was, for a certain time of his life, a dedicated communist. He was also one of the founding fathers of population genetics and therefore all of mathematical biology. This is a theory which formulates cooperation between relatives, and we have to ask the question, how can we get any kind of cooperation between non-relatives? And in order to do this, we have to have a closer look at the game-theoretic situation that describes cooperation. And the appropriate game-theoretic formulation is called the prisoner's dilemma. Game theory is a discipline of mathematics that was invented by John von Neumann and Oskar Morgenstern, working together in Princeton in order to describe mathematically strategic and behavioral decisions of humans. They had games in mind like poker or other things. But it was later, there was a game invented by people at the Rand Foundation in California, which is called the Prisoner's Dilemma. And the Prisoner's Dilemma is a game about cooperation and defection. And it is called Prisoner's Dilemma for some reason that is actually totally unimportant. Let's just concentrate on what the game is. So you can either cooperate or defect. If we both cooperate, we both get 3 points. But if I cooperate and you defect, I get 0 points and you get 5 points. If I defect and you cooperate, I get 5 points and you get 0 points. And if we both defect, we both get 1 point. So if you now look at this game, you have to make a decision. You have to imagine yourself playing this game with me or with somebody else, and you want to decide, would you like to cooperate or would you like to defect? So you should look at these payoff values and then decide to cooperate or to defect. And if you analyze the game as a mathematician would analyze, in a kind of the definition of rationality here, that you want to maximize your payoff, then you analyze it in the following way. If you assume that I will cooperate, you have a choice between getting 3 points if you cooperate or 5 points if you defect. So under the assumption I will cooperate, it is better for you to defect. But if you go here under the assumption that I will defect, you have a choice between getting 0 points or 1 point. It's still better to defect. So no matter what you assume I will be doing, it's better for you to defect. And if I analyze the game in the same way, we both end up with defection. This is called rational players choose defection. And the strange thing is that we would have been better off if we would not have analyzed this game in this way, if we would have cooperated, but cooperation is irrational. And I don't want to offend anybody here. I had this experience with students who were offended by the statement of rationality and irrationality. This just uses the definition of game theory for rationality. A rational player is one who looks at the numbers and behaves in order to maximize his or her return. A rational player is somebody who wants to get the most points. So game theory makes the assumption what is written down here is what people want, and then they ask, what is the strategy that gets you the most? And the strange thing in this game, the strategy that gets you the most is to defect. We would have been better off if we would not have been so greedy and instead cooperated, we would have gotten even more. That's the surprising thing. And now the nice thing about evolutionary game theory is that this notion of rationality, we don't actually need it. In evolutionary game theory, you can just build a population that consists of cooperators and defectors. Say half of us are cooperators, half are defectors. They play randomly with each other. We count the points, and we reward those who have more points by, for example, they produce more offspring. They reproduce. They can either reproduce genetically or they can reproduce culturally. So I see somebody having many more points than I have, so I try to ask myself, which strategy does he use? And I will try to imitate this strategy. So strategies can spread by genetic rules or behavioral rules, or by cultural rules. So if you do this, if you have a population of cooperators and defectors, the interesting observation is defectors always have a higher fitness than cooperators. Because whenever they meet another cooperator, they get more than if a cooperator would have met that cooperator. And if they meet another defector, they also get more than if a cooperator would have met that defector. So regardless of the analysis, there's no need to make an argument of rationality. Just players who play a fixed strategy of cooperators or defectors, natural selection will favor defectors. This is the dilemma. Therefore, we need a mechanism for the evolution of cooperation. When we observe cooperation in a biological system, we have to ask ourselves, what is the mechanism that has led to cooperation? And the first mechanism that I suggested was kin selection. Kin selection is the idea that you help those who are related to you, genetically related. A second idea is group selection, and I will briefly mention group selection later in my talk. But what I would like to explore for most of my talk is reciprocity. And reciprocity is the idea that I help you and you help me. More precisely, we have one part of reciprocity is called direct reciprocity. In direct reciprocity, we assume there are repeated interactions between two individuals. We meet now, and I help you, but somehow I expect we will meet again, and then you can help me. This is the idea of direct reciprocity. And direct reciprocity is formulated as a repeated prisoner's dilemma. So we play the game not only once, as we discussed it just now, but we play it several times. If we play the game several times, you can no longer make a simple argument that the best thing is to defect. Because if I cooperate now, I could somehow induce you to cooperate on subsequent moves. Therefore, it is no longer the case that defection is just the best thing. On the other hand, it's a very complicated question to ask, what is a good strategy in this repeated prisoner's dilemma? And this question was asked by a political scientist at Ann Arbor University, Robert Axelrod, and he had a brilliant idea. He said, I would like to find out what a good strategy is for the repeated prisoner's dilemma. I will conduct a tournament. And in this tournament, people should submit strategies, and I will have them play against each other. All strategies play against each other. I count the points, and I will announce who gets the highest number of points. So in every single round, you have points, and you accumulate these points, and then you just add it up. And the big surprise was that he got 14 entries submitted from a mixture of mathematicians and so on, but the big surprise was that the simplest of all strategies won. And this simplest strategy was submitted by a famous game theorist, Anatol Rapoport, and this was only a program of 5 lines, and it works in the following way. I start to cooperate. I always start with a cooperative move, and then if you cooperate, I will cooperate in the next move. If you defect, I will defect in the next move. So I play whatever you did play in the last round. I just mirror your behavior in some sense. It's almost as if you were playing yourself. It was a surprise that the simplest strategy won, because some of the other strategies were smart. They sort of tried to use a Bayesian inference to predict what the other person would do. The simplest strategy won. Then he published these results, and he said, let's play again. Let's have a second round. And now he got 63 strategies. Many, many people looked at this, and many people submitted strategies that would have been clear winners of the first tournament, including John Maynard Smith. John Maynard Smith submitted a strategy for the second tournament, Tit-for-tat, which would have won the first tournament. Only one person had the idea to submit Tit-for-tat again, and this was Rapoport. And it won again. The surprising thing is it won again. So in the repeated prisoner's dilemma, it is possible to calculate a good strategy against a known set of opponents. It's very hard to predict against an unknown set of opponents. This was published, and Axelrod wrote a very famous book, Evolution of Cooperation, which is a brilliant book that I can recommend to everybody. And Tit-for-tat was a kind of world champion in the prisoner's dilemma. But soon it was realized that there was an Achilles heel. Tit-for-tat had one weakness. And the weakness was that if there are errors, these errors destroy cooperation. So if you imagine 2 Tit-for-tat players playing against each other, and by some unfortunate coincidence, one of them actually defects, then the other one will retaliate. There's now a series of mutual defections. If there's another mistake, it can lead to complete defection. You can prove mathematically that in the long run, Tit-for-tat players with an arbitrary small amount of noise get the same payoff as just random players. So they perform as purely as just flipping a coin on every move. This was the Achilles heel of Tit-for-tat. It cannot correct errors. The payoff that Tit-for-tat has is greatly reduced in a scenario where errors are likely. And errors are always important when you look at a biological situation, where sort of your intention to cooperate gets misinterpreted or something like this. Or you mistake with whom you had the interaction last time. So therefore, we wanted to come up with a framework where natural selection would choose its own strategy. Natural selection, rather than a set of experts, should choose a strategy in an erroneous, in a noisy environment. So we set up a computer simulation that started with a random ensemble of strategies. In a random ensemble of strategies, the best thing to do, and the first strategy that started to dominate, was always defect. So if there's sort of no organization, if people just play random moves, again, the best thing is to do defect. But fortunately for this research program, this was not the end. And what was very nice, then when it looked like as if always defect had almost completely won, there was an invasion by a small minority of Tit-for-tat players, and these Tit-for-tat players took away completely the population toward Tit-for-tat. And the situation is now, if almost everybody is playing always defect, and a small cluster is playing Tit-for-tat, then they will help each other. When they meet each other, they get a high payoff. with always defect, they are not really exploited because they retaliate once they realize always defect is defecting, and therefore they have actually a good chance of taking over. And this was expected because it was known that tit-for-tat was a good strategy. The next few moves were then more surprising. So what happened, tit-for-tat was only there for a very short time. And then this program generated another strategy which hadn't been described before, and this was generous tit-for-tat. Tit-for-tat was immediately replaced by a strategy that was much more generous, and generous tit-for-tat works in the following way. If you cooperate, then I will cooperate. But if you defect, then I will cooperate with probability 1/3. So at times, I will cooperate even if you defect. And the reason for this is because then if you defect accidentally, I can correct for this mistake. So the idea here is never forget a good move, but sometimes forgive a bad move. So this is like a natural selection leading to a certain level of forgiveness. It was just tit-for-tat, so I do whatever you did, but here, in addition to this, I will forgive. And this strategy was chosen by natural selection because it can correct mistakes. It has a much higher payoff in a noisy environment when playing itself or when playing tit-for-tat. But again, the game was not over, and what came next was also a surprise. Generous tit-for-tat was replaced by always cooperate. And the reason is the following. If you imagine everybody in this room playing either tit-for-tat or generous tit-for-tat, and like 10% of people play always cooperate, then in this society, everybody is nice. Nobody tries to exploit the other person. So there's no disadvantage for those who just unconditionally cooperate. And as you can imagine, a biological trait which is not under selection to be maintained will be lost. You just lose a trait that you don't use. These people somehow, they don't use the trait to retaliate because nobody's trying to cheat on them. So the population drifts with random drift, with neutral evolution to always cooperate. But once everybody here is cooperating, you really invite the invasion of always defect. And in this simple computer program, you have a model of human history. You have oscillations of war and peace. And this is a typical phenomenon of studying evolution of prisoner's dilemma. And there's never a stable solution that leads to cooperation. Whatever I have tried in many, many different frameworks, it's always oscillations. You always get oscillations because once you have a society that more or less protects itself against defectors, it will be undermined by unconditional cooperators. And they invite again, so they are too peaceful then, and they invite again invasion of defectors. In that simple version of the program, there was one strategy that did break the cycle for a short amount of time, and this was a new concept in the repeated prisoner's dilemma, and this strategy is called win, stay, lose, shift. And win, stay, lose, shift works in the following way. Whenever you are doing well, you continue with what you have done. When you are doing badly, you change. So you have a certain aspiration level, and the optimum aspiration level you can prove here is you want at least 3 points in this game. If you get 3 points, you just continue. So if you have cooperated against the cooperator, you are very happy, you continue to cooperate. If you have defected against the cooperator, you are happy because you have 5 points, you continue to defect. But if you cooperate against the defector, you have only 0 points, you're unhappy, you change from cooperation to defection. And here you defect against the defector, you get only 1 point, you're also unhappy, you change from defection to cooperation. So this is win, stay, and lose, shift. And this is a null hypothesis that is used by animal behavior people to understand what they see. So if they observe a certain action, they would ask, is it like win, stay, lose, shift? So it's a very fundamental instinct that many animals are expected to have. It's therefore very interesting that this strategy does amazingly well in the repeated prisoner's dilemma. So win, stay, lose, shift has the following advantages. First of all, it can correct errors, because if there are 2 win, stay, lose, shift players playing against each other, by mistake I defect, then I realize, oh, that was good that I defect again, but then both of us get hit, and we're both unhappy, and we switch back to cooperation. So this is like there was a random event that caused an argument, but after this disagreement, we're friends again. It's like a machine, a deterministic machine to correct occasional disagreements. If you have win, stay, lose, shift playing always cooperate, after some time you realize that always cooperate can be exploited, and you exploit it. Therefore, the population does not have the weakness that tit-for-tat has. This is a strategy which sort of I find ethically kind of bad, but what it achieves is that the population is stable in the cooperation regime. It also, like tit-for-tat, it can resist invasion by all T, so it defects on every other round. So it has one advantage over tit-for-tat, it can correct errors. It has another advantage over tit-for-tat and generous tit-for-tat. It can dominate all C, and this it has in common with tit-for-tat and generous tit-for-tat. However, you can prove that generous tit-for-tat is the best catalyst for the emergence of cooperation. No other strategy is that well able to induce cooperation in a society where almost everybody is defecting. In a society where almost everybody is defecting, tit-for-tat is usually the best starting point for a cooperative regime to emerge. But once tit-for-tat has been established, it gets replaced by generous tit-for-tat and win-stay-lose shift. So usually the story of the prisoner's dilemma is thought to be by many people a story of tit-for-tat. Most people think that this is the main strategy. It was also actually shown by economists at Harvard University, Drew Fudenberg and Eric Maskin, that win-stay-lose shift is the only weak, evolutionarily stable strategy among simple strategies playing the prisoner's dilemma. So you can even prove mathematically that tit-for-tat does not have this stability concept. This is a stability concept that was introduced by John Maynard Smith. And John Maynard Smith, the famous evolutionary biologist who worked at the University of Sussex and was, of course, also a fellow of the Royal Society, he invented evolutionary game theory. He introduced the concept of an ESS, which is similar to a Nash equilibrium. And a strategy is an ESS when a whole population adopting it cannot be replaced by a small amount of mutants. So win-stay-lose shift has this property, but not tit-for-tat. I have talked about theory only so far. And this is also my talk, but I should mention that this is also an area of many, many empirical investigations. There are many experiments being performed with lots of animals and also with humans, students. And my favorite experiment was something which was published in Nature more than 20 years ago, and this was an experiment by Manfred Milinski, and he observed cooperation among sticklebacks inspecting a predator. So this here is a pike, and the pike eats these smaller fish, sticklebacks. So when these sticklebacks see a pike, they do not swim away, as you would think is the best thing to do. In fact, they swim towards it. They swim towards it because they have to inspect it. They have to be sure that this is a dangerous predator. Maybe it's just a stick of wood or something like this. And also they have to assess the situation of danger. Is this a predator who is hunting or sleeping? Or in a normal environment, they cannot adopt the strategy of just swimming away because there are too many things that look like pikes and there are too many pikes around. So this behavior is called predator inspection behavior. They have to find out whether the situation is dangerous such that they have to leave or can continue to forage. Now, usually when they do this in pairs. And now this becomes a game which is a prisoner's dilemma between these two sticklebacks here, because if I defect, then I stay a little bit behind and I let you go forward to assess the situation. And from a safe distance, I will observe what happens. And if the predator attacks you, I know the situation was dangerous. And on the other hand, if we both cooperate, we both move forward, and this induces a predator confusion effect. So it can be measured that a predator has a smaller chance to get one of two than one of one, because then the predator to the last moment isn't really sure for which fish to go for. So it's a game of cooperation defection between these two sticklebacks. And Manfred Milinski had the ingenious experiment of using a mirror actually to suggest to this stickleback a mirror image of its own. And if the mirror was straight, it was a cooperating partner. And if the mirror was in an angle, it was a defecting partner that swam away, that stayed behind. So by moving the mirror, he could actually play tit-for-tat or win-stay-lose shift with these animals, and found that they had kind of tit-for-tat and win-stay-lose shift-like behavior in the predator inspection. As I said, such experiments are also performed with students. And there are many experiments on the prisoner's dilemma, and there's a big field, experimental economics, and people are also doing brain images of people while they cooperate or do defect to understand which regions of the brain are involved in such decisions. And it has to do with delayed gratification, actually. So if you cooperate, you're somehow investing in a future return than getting everything immediately. That's an idea. Another area of reciprocity is indirect reciprocity. Direct reciprocity was the idea that we have repeated encounters. I help you, and then you can help me. But many encounters that we have are not of this kind. We might meet somebody, and we have a choice to help or not to help, not expecting to be reciprocated by that very person on some future occasion. Nevertheless, it's our intention to help. It's our intention to help a stranger who asks for directions or something like this. So the idea is indirect reciprocity. And this is that I will help you, and somehow I expect somebody else will help me. I will not get the reciprocation directly from you, but from somebody else. So how does this work? So in principle, there are two forms of indirect reciprocity. One form is that a player A helps a player B, and B is now so happy because he just received a favor that he goes out and helps some person C. This is a very natural form of indirect reciprocity, and somehow people seem to do this in an experiment. Interestingly, theory cannot yet explain this. We have actually no theoretical explanation for this kind of indirect reciprocity yet. But the following kind of indirect reciprocity works. A helps B, the situation is observed by somebody C, and then C helps A. So the idea would be that the donor can cooperate. If the donor cooperates, the donor pays a cost, and the recipient gets a benefit. If I do this, there is a so-called reputation. My reputation increases. If I don't do this, my reputation decreases. So you help somebody, you get the reputation of a helpful person, and the question is, does the society work in such a way that we tend to help people of whom we know that they were helpful? So we set up the same computer simulation as for the repeated prisoner's dilemma and found that natural selection indeed designed strategies that based their decision to cooperate or not on the reputation of the recipient. So as we had first observed tit-for-tat and generous tit-for-tat in direct reciprocity, here we observed strategies that monitor events that are going on between other people and then target their help towards those that have given help. This makes a lot of sense for us. In the repeated prisoner's dilemma, you have to use your own experience with somebody to decide what to do next. But here you use the experience of others. You have others playing the game, and you just observe what the outcome is and then decide who is a cooperator or who not. Or even more than this, you continuously talk to your friends and others to find out how exactly was your interaction with this person? What do you think of this person? Should I go and work for him or something like this? A large part of our coffee table conversation is devoted to talk about others. We constantly seem to be interested in monitoring the reputation of other people. So there's a possibility to have a co-evolution of this type of cooperation and human language. Human language is very important for this type of indirect reciprocity. It's interesting to note that even though the calculation is totally different, a simple rule emerged for indirect reciprocity that can be compared with Hamilton's rule, and it only works if the probability to know somebody's reputation exceeds the cost-to-benefit ratio. In Hamilton's kin selection theory, this was the coefficient of relationship. And here it is the chance that you know somebody's reputation. If the society is completely anonymous, reputation doesn't work. There's also a mathematical joke here that actually you can set up the model such that there is a universal constant of nature emerging. There's a number which does not depend on any parameters whatsoever you put into that model. And this is the maximum fraction of people who can be bad in the beginning such that everyone will be good in the end. This also has sort of teleological consequences. Another kind of reciprocity, this is a reciprocity I explored specifically with Bob May when I had the privilege to work with him in Oxford, is spatial reciprocity. And this is the interaction between cooperators and defectors on a spatial grid. And here you get cooperation because the cooperators form clusters. So the idea is that you help your neighbor. So what we observe is that cooperators and defectors can coexist here without complicated strategies, without memory, without recognition of others. All of these things you really need for direct reciprocity and indirect reciprocity, but not for spatial reciprocity. Cooperators survive in clusters because cooperators in blue here, they form clusters, and the idea is you help your neighbor. And if you are a cluster, then your neighbor is also a cooperator. And mathematically, there are fascinating structures here. We observe spatial chaos and dynamic fractals and evolutionary kaleidoscopes. This is such a simulation of a deterministic automaton that started with a symmetric initial condition, and the symmetry is maintained because the transitions are symmetric of this cellular automaton. There's also something which I would like to mention briefly, and this is the revival of group selection. Group selection was introduced in the 1960s, and the idea is that if you form a group of cooperators, they do well. There was much discussion about this, and more people, and it was denied. Then after a famous book by George Williams, it was actually denied as an important mechanism of natural selection. But more and more people are coming back now to understand the power of group selection. And you can envisage a simple game where you play a game with others in your group. So the population is subdivided in a group. You play the game with others in your group. Offspring are added to the group. Groups divide when reaching a certain size, and groups die. So in this very natural situation, you get evolution of cooperation. In another, and this is also something which we're doing at the moment, you also get cooperation if the population that you study is not just a well-mixed population, as is normally assumed in population biology, but has a certain structure to it. So for example, I know certain people, and I have many more interactions with some people than with others, so there's a social network. So we imagine a game being played on a social network. The social network is described by a graph. On the nodes, on the vertices of the graph is where the individuals are, and the edges describe social interactions. And we are very much working toward a theory that tries to formulate which graphs promote evolution of cooperation. The nice thing for me is mathematically you can summarize all these laws for the evolution of cooperation in a simple form, and all the different theories, they lead to something very elegant which can then be compared with each other. So at the basis of every theory, there's a fundamental inequality that involves the cost-to-benefit ratio of the altruistic act. And this has to exceed another quantity. For example, here the coefficient of relationship. For direct reciprocity, the probability of playing another round. Here, the probability to know somebody. And these two equations are much newer, and we are still studying this thing. But also for group selection, there's a very simple mathematical formulation possible. And even for graphs, which is even more surprising. So much of my talk here was about evolutionary game theory. Game theory as an economic mathematical discipline was invented by John von Neumann and Oskar Morgenstern, but it was brought to biology by the seminal work of Bill Hamilton and Bob Trivers, and really invented as a biological subject by John Maynard Smith. It's a generic description of evolution whenever fitness is not constant but depends on others. When I started to do my PhD thesis on evolutionary game theory, I was embarrassed to tell my parents that I was working on games. So as time progressed, I realized that this is a very general framework that describes the generic aspect of evolutionary biology. So whenever fitness is not constant, but depends on what others are doing, this is what evolutionary game theory is. And a very important book is a book by Josef Hofbauer and Carl Sigmund. Josef Hofbauer is a professor at UCL now that describes the mathematical framework of evolutionary game theory in great and amazing detail. What is also brilliant for me, and this is a theorem which is stated in this book by Hofbauer and Sigmund, is very elegant. The fundamental equations of evolutionary game theory are identical to those of ecology. Ecology is described by Lotka-Volterra equations, and they translate one-to-one into the fundamental equations of evolutionary game theory. This means, for example, that a lot of the seminal early work that Robert May did in ecology has its counterpart, its mirror image in evolutionary game theory. He described cyclic interactions between species, and precisely this can also be found in game theoretic situations. And Christopher Seaman has also very much worked on this general subject. It's a beautiful and large mathematical theory that has many followers. I would like to talk very briefly about fairness. Maybe it is not appropriate to, or not necessary to talk to a British audience about fairness. But here is a game. The game is the Ultimatum game. And in the Ultimatum game, there are two people, and there's $1 million. And the person who conducts the experiment says to one person, you're the proposer, you can make an offer. The other person is the responder. The other person can say yes or no to this offer. So I ask you, please come here. We play this game now. Imagine in that other room is another person, and you will have to propose to that other person how to split this amount of money. You could say, let's split 50%. Or you could say, let's split 60% versus 40%. Whatever you do, if the other person says yes, it goes ahead. If the other person says no, it disappears. Right? I keep the money. Neither of you gets anything. So what would you do? Who would like to offer 50%? Who would like to offer more than 50%? Who would like to offer 40%? Or say 30%, 20%, 10%? Nobody wants to offer 10%? See, and now you have to imagine yourself being in the other room. Now you are in the other room, and suppose somebody has just offered you 10%. So somebody has just offered you $100,000. And you have a choice between accepting or saying no. So no means you don't get anything. Accepting means you get $100,000. So who would accept the $100,000 as a reciprocity? See, but nobody was willing to offer 10%. That's the interesting thing of this game. There's one disadvantage is that the game is usually played only not for $1 million, but only for $100. And this is because most people don't have a very big research budget that could support such experiments. But Harvard economists had the brilliant idea of taking $100 and going to a country where they could find people for whom $100 was 3 times their monthly salary. So you can imagine playing the game for 3 times your monthly salary. So a significant amount was involved in some of these experiments. What does game theory suggest? Game theory suggests that a rational responder should prefer $1 over $0. So if the other person over there was only rational, he should realize it's better to have $1 than to have $0. It is better to have $10 than to have $0. If I assume the other person is rational, a rational proposer should offer $1 and keep the whole sum. So you should offer the minimum possible amount and expect the other person has a choice now between nothing or whatever you have offered. Obviously, he should understand that it's better to take something than nothing. This is what game theory suggests. And what do the experiments show? People are not rational. Most proposers, so this is also the same in the prisoner's dilemma, people do cooperate. People are not rational. People don't follow rational game theoretic suggestions. Most proposers offer 30 to 50%, exactly as the audience here. Most proposers are between 30 and 50%. And they are well advised to do so because most responders reject offers below 30%. So in those experiments where you did play for 3 times your monthly salary, people were very willing to give away a month's salary if they had the feeling that something was an unfair deal. Better we insist on a fair deal, and better we have nothing at all than accepting an unfair situation. This is what is surprising. So we played the evolutionary ultimatum game. In the evolutionary ultimatum game, as for the prisoner's dilemma, you do not need rationality. We just have a population of strategies playing each other, and we see which strategy does better than which other strategy. And what we find, surprisingly, is that natural selection also chooses low offers and low demands. So there is no need to assume anything about rationality or irrationality if you play the game in a group where people follow certain strategies, and the strategy is, this is what I would offer, and this is what I would accept. So each player is described by 2 parameters only. Then what you get by natural selection is that those players do well that offer almost nothing and accept almost everything. And the reason is, in any encounter, it costs to reject an offer. So if I have just rejected an offer, somebody else might have accepted that same offer, so somebody else has actually had an income while I had no income. So it costs to reject an offer. Therefore, natural selection prefers low acceptance levels. If the acceptance levels drop, it costs to make an unnecessarily high offer. The offer drops also. So without invoking any notion of rationality, natural selection also leads to unfair solutions. So how can we explain the evolution of fairness? And again, with a reputation. Suppose there's a small chance that it will become known what offer a person has accepted. That changes the situation completely, because now accepting low offers increases the probability of receiving reduced offers in the future. So if I'm known to accept whatever you offer me, and if there's some chance that you might find out that actually you're playing the game with me, then you could well offer me something low. If I know that some person has never accepted anything less than 50%, I would be very daring to do so, to offer less than 50%. So basically, rejecting low offers is costly, but it buys the reputation of being someone who demands a fair share. So people behave in the ultimatum game. They do not really buy the promise that this is a strictly anonymous situation. because such situations do not exist in real life. In most situations, somebody is watching. Somebody will find out. I might tell somebody. I might go home and say, this person offered me 20% and I rejected it. And in that sense, reputation here leads to fairness. So this study on the evolution of fairness was also done with Carl Sigmund, as many other things in this talk, and also with Karen Page, who is a lecturer at UCL here in London. I would like to make a few remarks now on the cooperation between science and religion, because my talk had to do with cooperation and with altruism. And this talk, as was announced by the chairman, this series of talks is sponsored by the John Templeton Foundation. And the John Templeton Foundation is very interested in promoting a meaningful dialogue between science and religion. We talked here about topics of cooperation and fairness. And obviously, this leads us to questions of ethics and altruism and altruistic love. So one goal of the Templeton Foundation is to promote the interaction between science and theology. And I think this is an important endeavor because both disciplines have much to offer for humanity. Religion is a universal trait of humans. All civilizations have invented religion. All civilizations have come up with religion. Religion is as fundamental to humans as is language. And religion is perhaps as old as language. And maybe it was one of the ignition points for language. Maybe the first things that people had to talk about was about mythological explanations and religious explanations. So there's a universal tendency toward religion as there is toward language. And we could even attempt to formulate looking for a universal grammar of religion. Like Chomsky asked the question, what is common to all human languages? We could ask what is common to all human religions. We could ask the question, what is a religious explanation that people accept and what is one that people would not accept as a religious statement? It is impossible for us to deny the enormous importance that religion has played in human evolution and human history. As we all know, some of the earliest artifacts of human civilizations have religious contents. So at times, religions are also suppressed, but such attempts have never succeeded. So for example, in the prime time of the Soviet Union, there were never more members of the Communist Party as there were illegal and suppressed followers of the Russian Orthodox Church. So even if the government has a very strong bias against religion, it doesn't succeed. In the United States, for example, today, it was mentioned by Charles Harper at a meeting recently, the largest fraction or the majority of all donations that are given to charities by people are for religious organizations, much more than for medical or scientific or other purposes. So why is this the case? We have to ask the question what it is that drives people to religious belief and activity, and actually science has a very good point to explore such questions, as aspects of human psychology. My own perspective is very positive. I think that religion alone gives purpose, which science does not really. Religion makes the trajectory of individual human lives uniquely precious. Religion makes the whole creation unfold like a beautiful symphony toward a certain goal. Religion is an enormous force for the good. Religion preaches cooperation and fairness, altruism and unlimited love. It actually wants to induce a love that goes beyond boundaries to encompass all human beings and the creation. Religion gives hope when there's despair, and we all need hope. Over the centuries, religion has inspired art and science. For Darwin, for example, it is remarkable, but there were two possibilities. And this is well described in the first edition of The Origin of Species. So the two possibilities were either God conceived everything in the beginning and equipped the universe with such elegant rules that everything else would follow by natural causes, or God has to perform a small miracle whenever he wanted to come up with a new species. Now, Darwin's whole endeavor was to provide scientific evidence for the first perspective and against the second perspective. But in both perspectives, there was God. So the motivation for Darwin's work was theological, you could argue. And this thinking was certainly a consequence of his time. There's no doubt that the biological properties of all living systems are ultimately explained by evolutionary causes. So evolution has led from single molecules to the human brain, Evolution has generated a being that has invented science and religion. Therefore, evolution led to both science and religion. And this is also another reason why science and religion should actually cooperate. These are the cooperators to whom I'm indebted as collaborators in my efforts and on this talk here and so on. And my teachers, I would like to mention Carl Sigmund at the University of Vienna, who was a PhD advisor, and then Lord Mayo of Oxford, your illustrious president of the Royal Society, defender of science. And I'm working, as it was mentioned by the chairman, at the Program for Evolutionary Dynamics, and we have a number of research projects, but I don't have to enlist them here. We are completely open-minded and work on whatever can be published in Nature and Science. Thank you very much.
Martin, you ranged over a large number of topics, but I suspect wisely stayed off politics. We're all living in a highly charged political environment in this country at the moment. It strikes me that some of our politicians would benefit from a lecture in game theory from you. But thank you for that lecture, and I gather you will accept questions from the audience. So if anybody has a question, would you please put up your hand? It will then take a moment for two people with microphones are present in the hall. There's one here. Could you put your hand up again, just here? And when the microphone comes, if you wouldn't mind just waiting a moment and standing up while the people wielding the web cameras can actually find you. And then who was the person over here? There's another microphone there. You will be the second in order. Thank you.
Thank you for your stimulating talk. I'm wondering how much it's limited, however, by the present state of computer developments, that we're just in the generation where it's easy to model these, in fact, very simplistic models of human interaction. And philosophically or spiritually, I'm concerned that your model assumes some external factor has to be introduced to explain it. You suggested we need to think about Darwin. My understanding is that Darwin was a very diplomatic atheist. However, that might be debated. But why do you have to posit that because Darwin said there is always competition in evolution, that therefore we have to, quote, need a mechanism from the outside for the evolution of cooperation? Why is it not possibly the case that the dialectical interaction of cooperation and competition between all sorts of life forms, material and living, actually creates an ever-increasing proliferation of complexity, which does not need some external mechanism to explain, my goodness, why are we here? And isn't religion, the religious feeling, part of that proliferation that makes such an enormously complex society, of which we're just one meeting this evening?
So the first part of your question is what the influence of computers were on this subject. And I can say that the development of computers, that was extremely important precisely for this type of subject. Because most of the simplest equations of evolutionary dynamics, unless even very complicated mathematical theories in physics, are nonlinear. Whereas in quantum mechanics, you have linear equations. Nonlinear equations very often need computer simulations, at least at first. So what we always do at first, we want to simulate something. Once we see what is happening in that system, we try to prove it. It is usually impossible to prove without having seen what is possible in a nonlinear system. So computers are very important for this. And for the second part of your talk, I would argue that what I'm trying to do is precisely what you have also argued for, that I do explain the evolution of cooperation without an external mechanism. So I just use the very basic ingredients of Darwinian theory of population biology. I use populations, I use mutation, I use selection, I use interactions, reproduction. I don't use anything else. So there is very much an internal mechanism that leads to cooperation.
Thank you, Martin. There was a question at the back here, and there was another one here. So could the microphone come here for the third question, and then we'll take your question now. Thank you.
It seems a shame not to plug the gap that David Reed has just identified. So, Martin, I wondered if you could comment on what you feel the implications are of indirect reciprocity, that is, where your behaviour is being observed by others, what the implications might be for international relations, say, for example, in the case of whether international cooperation is better served by countries that talk to others or by countries that invade others.
So I must admit that I was always totally pro-American in my political perspective and was totally disappointed with the Iraq war, for example, which I felt was not really justified. That changed my point of view completely, actually, and disappointed me very, very much. And I also thought deeply about what is, in fact, the interaction between countries, and why is the interaction between countries different to the interaction with my neighbor? So if I have a disagreement with my neighbor and we cannot resolve it, I will not invade. I will not start the war with my. It's impossible. Instead, there will be like a court or something like this. You might have a lawsuit or something like this. But why is it that countries always resolve to brute force when they cannot resolve a conflict? And I talked to lawyers, actually, at Harvard. And so one idea is that if you are on the level of a country, there's sort of nothing above. There's nothing more powerful than you. So the most powerful country certainly doesn't want to accept any other instantiation that would rule over it, because it would think it's sort of smart enough to make its own decision. So you are on the top level of sorting out conflicts and creating conflicts. And here is where it is much less cooperative than if you are on a lower level, where there's essentially a hierarchy to which you can refer if you cannot resolve your conflict. I think what we desperately need is that countries recognize an international court that is effective and that can decide and resolve conflicts. And there have been examples where there was a conflict, I think, between Israel and another country, and there was a court involved, and the court had a decision against Israel, and Israel accepted. But these are rare examples.
Isn't it the case that as humans you collaborate with those that you know? And the more distant the community, the less likely you are, the more you feel those people are defective.
I think with the internet we have a great chance to get to know to many other people, and the interactions are much better. In our small group of scientists, I think we also have the chance to build up international relations that are somehow deep on a personal level, because scientific groups always consist of people from all different countries.
Thank you. Where did the microphone end up? There. Yes, and just before you start, is there another question on this side? Yes, one here. If you could bring Catherine.
Charles Downs.
And then Charles, yes. This gentleman, will you put your hand up? And Catherine will pass the microphone, then we'll come to Charles. You first. Thank you.
Okay, I've got two if I can get away with it. But the first one is, the general drift of what you're saying seems to be that the more information players have about one another, the better their intelligence, their memory, the greater the incentive to morality or cooperation. How that fits in with the alternative way of diffusing mega competition, which is the ability of the players to refuse to play or to hide from one another, I'm not quite sure. And it seems to me that there's some kind of tension between increasing cooperation by being able to refuse to play and increasing cooperation by everybody knowing virtually everything about everybody else. Has this been modelled, and is there a resolution to it yet?
Yes, so there are two different aspects to your question. The first is, do you get more cooperation when you refuse to play? And the answer is yes. That has been modelled, and that works very nicely. So if the strategy is cooperate or defect or not play at all, in that scenario, you have more tendency toward cooperation. This is a kind of weak mechanism that increases the amount of cooperation. And so that was published. And the other, what was the other?
So those aren't necessarily antagonistic, having more knowledge and refusing to play.
No, that's right.
Okay.
Yes, that's right. And so the other question was?
Well, I think if I was...
Oh, that's right, the general information. So usually the more information, the better, because this helps you to identify the cooperators. The question is how well the system can be abused by defectors to feed in false information about them to appear as cooperators.
Yeah. Okay, this partly relates to my second point in the payoff for appearing to be a sucker. For example, if I, as a member of an accredited religion, am categorised as a sucker by many other players, they may actually deal with me more. And so they may come to my fruit shop or whatever, and even though I'm selling at a lower rate, they may see me as someone who's more frequently worth interacting with. And since they're interacting with me rather than the toughies, then again, I can win in the long run, like the special needs child who always accepted a 2p instead of a 5p, because he knew that if he accepted a 5p, people would stop demonstrating his own stupidity. If that's... Okay.
So is your observation that if people realize that you can be exploited, they prefer to interact with you and therefore exploit you even more?
I think if they feel they're less likely to be hammered, they're more not likely to interact. And interaction creates a possibility of more payoffs, given everything that you've said so far.
Yes,
so not looking too tough may pay well in some parts of London, although where I come from in Holston, I have my doubts about it.
Yeah, so it's a good point. So the one thing is you want to have the reputation of somebody who is a cooperator, but you do not want to have the reputation of somebody who is very happy to be exploited.
But being a slight sucker might actually pay off to be perceived as a slight sucker.
That could be.
So I think we'll take two more questions. There was one at the back. Somebody has a... Yes, you have a microphone. Would you like to? And then we'll take one from Charles, and that will probably be the end.
Yes, I wonder if you would like to comment on the possible way in which religious or other cultural systems might interplay and feed back into biological evolution and genetic selection.
I mean, you could argue that religion was something which was there very early in human evolution and therefore had a strong selective force on language, on culture, on other aspects, promoted exploring the world with scientific methods and also promoted art. So in this sense, you can say that religion had a very strong influence on the cultural evolution of humans. It is unclear whether over such short time scale you would also expect to see an influence on the genetic evolution.
Thank you. And I think just one more question, Charles, to round it up. Thank you.
In the case of one person giving a certain fraction of his money, a certain fraction of $100 to another group, I think I understood what you had to say about the probability of choices and so on. But it wasn't clear to me that you considered what that did in the long run to the group relationships or to the relationships. Did you make any comment about that? Or was there any conclusion about that at all?
So which other interactions?
In the long run, the long run, after, if people make a choice to take 10% or 50%, so on, in the long run, what does that do to the groups of people involved?
You mean in the ultimatum game?
Yes.
Yeah, so the idea would be if you are somebody who is accepting 10% and the word spreads that you are accepting 10%, people will know that they only have to offer you 10%. If the word gets out, you have never accepted anything less than 50%, then people will offer you 50%. So the interesting thing in that game is also what is known for other games, that you can reverse the situation by committing yourself, by forcing the opponent in a choice situation. So for example, you could say, hang on, before you make me any offer, I tell you, unless you offer me 90%, I will not accept it. And this is a strategy which is sometimes used by political leaders even, when they say that I have committed myself so much that I definitely will start the war or something like this, should you attack me. And I will lose every recognition if I do not do this. So this is often observed in game theory, that you race into a situation where you force the other one to have a choice, and you have already committed yourself.
But you didn't make a conclusion as what the ultimate success would be for the two groups.
So then that has not been explored. The ultimatum game in the context of a group selection scenario has not been explored, and that would be an interesting research project.
Good. Well, I'm getting signals which I believe indicate to me that whereas we have all cooperated very effectively in response to your excellent lecture, Martin, there are defectors up there who tell us that the webcast broadcast should have finished some while ago. I apologize to them if we've broken any rules of transmission, but on behalf of this audience that has responded so excellently to your superb talk, thank you very much indeed, Martin. And also, just before I finish, we will combine the traditional applause for Martin with a vote of thanks for the John Templeton Foundation. We very much appreciate your generosity in enabling us to run this series of lectures, which are indeed inspiring to all of us who are involved in the scientific endeavour. Thank you very much, the John Templeton Foundation.